Alright guys, welcome back. This is part 2 of lecture 5 concerning angular momentum. Show an example of angular momentum in play.
The team final she was good, but here she was spectacular. And what made this exercise so wonderful were her handstand positions right there on top, but also the release skills. Generated great excitement in the arena. So look at the height on this one, and then she'll connect it. Absolutely gorgeous. Realize when she's doing every single muscle is tight and flexed.
The question is, this score, 15.733. Question is, this score, 15.733.
Okay, the dismount is the part I really want to focus on here. And I'm going to go back because it didn't really play super well. We'll try that again. Oh, that was even. Let's try it one more time. Okay, you get a better idea of what's going on there. So as she dismounted the bar, she chose to use what's known as the open position, where she did not tuck her body. And I want to talk about the consequences of that in terms of angular momentum. Should have probably mentioned in the last slide, but that was Gabby Douglas, the American gymnast who won gold at the 2012 London Olympics. She is awesome. We want to talk about the physics of what she did there. The first thing I want to think about is what period of time is best to analyze. For what we're doing, I want to look at the dismount only. So this is only from the period where she releases the bar, but before she hits the ground. So she is a projectile for all of these questions. So is her translational momentum conserved? Well, that would only be true if the external net force acting on her was 0. And remember, she's an extended body, so we just treat her as a particle where all of her mass is concentrated at her center of mass. So her momentum is only conserved translationally if there is a net force of 0 on her center of mass. So no, absolutely not, because there is a gravitational force that's accelerating her downwards at a rate of 9.8 meters per second squared, or 10, as we often use in class. What about our angular momentum? Would that be conserved? Well, like we talked about in the last video, angular momentum is only conserved if the net torque is 0. So torques always come from forces. The only force is gravity. So when is the torque of gravity equal to 0? Really simplified model, so we can try to determine just in general when is the torque of gravity 0 and when is it non-zero. So I'm going to start with just a rod on a pivot. And I'm going to split the rod down the center. I'm not actually going to cut it. It's still, attached to itself, or whatever you want to say. But I'm doing this because I want to show you there's two equivalent ways that you can sort of answer this question. So first, each side has the same amount of mass, the same length, the same density, the same everything. They are identical in every way. We want to now determine what is the net torque on the system. Lengths are the same. And the gravitational force always originates, or I should say its vector, always originates at the center of mass. So since I'm treating these like it's two separate objects, I'm going to have two separate gravitational forces, each at the center of mass. Well, does each of these torques necessarily have to be the same in magnitude? That would depend on what the torque formula tells us. Torque is equal to RF sine of theta, where theta is the angle between R and F. R, remember, is the position vector. It runs from the center of rotation, here that's the center of mass of the entire rod, out to the point where force is applied, and then down the length of the force, in the direction of the force. Well, that's a 90-degree angle then. And so for both of these, we have the same R value. These are the same length, right? And they're centered here. So the center of each half of the rod is the same distance from this dotted black line. The force will be the same because it's the force of gravity, and that's proportional to an object's mass. Each side has the same mass. And theta is the same. It's 90 degrees on both sides, and the sine of 90 is 1. So they both exert the same magnitude of torque, but I'm saying that the counterclockwise direction is positive, like we did in class. And therefore, this is a negative torque here on the right side, and the net torque is 0. That means two important things. One, the system has 0 angular acceleration, and 2, it has conserved angular momentum. Equivalent way to set this problem up, it gives the same answer. I'm going to get rid of all this stuff. And the change I want to make is I don't want to think of it like it's two different rods attached. I want to just say it's one rod and analyze it that way. If we have only one rod, we'll say it's got length L. It's obviously a different L than the last problem because it wouldn't be equivalent, but it's just L. It doesn't matter. The gravitational force is going to act in the center of mass of this entire rod, or here, and therefore the gravitational torque also acts here. But now let's think about the formula for torque. RF sine theta. Well, F, the force of gravity, is going to be the entire mass of the rod times the acceleration of gravity. Theta, still 90 degrees, but what's R? What's the distance between the pivot, or the axis of rotation, and the point at which the force is applied? 0. They both are right here, and therefore there would be 0 gravitational torque, and the net torque would again be 0. And that's consistent with what we proved by splitting the rod up and analyzing it that way. What if we do what if we say that this rod is not balanced on a pivot in its center, but instead we shift the pivot over here to the right such that it's 1/4 of the length of the rod from the right side, or sort of equivalently 3/4 of the length from the left side. How would that change our answer? Well, we could still do one of two ways. We could sort of split this into two rods, one of length 3L, one of length L, or we could just continue to say it's one rod of length, I guess, 4L now, and just put a single gravitational force vector at the center of mass. And if we do that, we see that everything stayed the same from the last question, except that the R value is no longer 0, right? This is the point at which the force is said to act, even though gravity really acts over the entire length. We treat it functionally as if it only acts at the center of mass here. But that is no longer a distance of 0 from the pivot, and therefore it's no longer a torque of 0. In this situation, again, taking counterclockwise to be positive, we have a non-zero torque in the positive direction. So here's an example where the gravitational torque was non-zero. So all that stuff we just did was to prove a very simple idea. Gravitational torque can be 0 or non-zero, but what does it depend on? Gravitational torque is only 0 when an object rotates about its center of mass. So what about Gabby? Let's go back to Gabby. Was she rotating about her center of mass? This all hinges on the first thing we said about her during the dismount. She is a projectile. The very good people at the Massachusetts Institute of Technology put together this presentation to show what happens when an extended body is moving as a projectile while rotating. So I know this video isn't super high quality, but if you couldn't tell, what happened was what you would expect if you throw an asymmetrically balanced object. It sort of rotated in a kind of a wonky way. You know, it wasn't rotating around its geometric center. But what if you were to paint the center of mass with orange, like it says here, and then turn off the lights and just watch the orange paint move under black light? Would we still see the same motion? Pretty remarkable, right? I mean, it's an indistinguishable trajectory from a true point particle. And what that says to us is that the center of mass of anything, whether it's a rotating extended body or a particle, the center of mass just follows a traditional parabolic trajectory. And the rotation is always around the center of mass.